Hello there. We're going to talk about implicit differentiation today. So in your notes, I want you to find this implicit differentiation notes day. And we're going to talk about that. So what is implicit differentiation? Normally, when we are dealing with graphs, we're dealing with functions. Y equals x squared, g of x equals sine x. But all of them are things that you could get into like y equals form, and they pass the vertical line test. But that's not all the graphs we can have. We can have graphs that are written with x and y commingled together. Sometimes you can pull y out, sometimes you can't. And that's when we talk about relations and implicitly defined relations. So implicit differentiation is basically for when you have x and y together rather than something in y equals form. Okay, and we can take derivatives of those things, we can find their slope, we can find tangent lines, all the things that we've been doing, but we need to change up how we do it a little bit. So let's start with an implicitly defined relation that you're all familiar with, a circle. So if I have the circle x squared plus y squared equals 9, that's centered at the origin, it's got a radius of 3. If we wanted to find tangent lines to this, I would need xy slope, means I would need the derivative. But I can't get this derivative right now because it's not in y equals form. So if we said, all right, well then let's get it in y equals form. Let's write this relation as a pair of functions. Let's get it in y equals form. I'd subtract x from both sides. And then I'd square root both sides. But I'd remember the rule that says if I create a square root that did not exist before, I have to give it a plus or minus. So that circle can be written as two functions, y equals the positive square root of 9 minus x squared, and y equals the negative square root of 9 minus x squared. And they both start and stop right there on the x-axis. Okay. Well, then what if I wanted to find tangent lines? I'd need the derivative. So if I want to take the derivative of y equals plus or minus the square root of 9 minus x squared, I'm going to think of that as 9 minus x squared to the 1/2, which means I am going to say dy dx is plus or minus, okay, chain rule, bring down the power, reduce it by 1, multiply by the derivative of the inside. And if I wanted to clean that up a little bit, if you ever have a plus minus multiplied by a negative, you can make it a minus plus. Doesn't always matter, but I'm going to do it anyway. And then 2 times 1/2 is 1, and so this is really x times 9 minus x squared to the negative 1/2. And that plus minus can be a plus minus or a minus plus. In this case, it does not matter. Okay, so I have two functions. I have two derivatives. The negative derivative and the positive derivative. That's cool. But that's also kind of annoying. I had to solve for y before I did everything. And there is a way to do calculus without solving for y. And in walks implicit differentiation. Okay, so I'm going to start this by just doing implicit differentiation, doing what you need to do, and then I'll explain it later. Okay, so implicit differentiation works like this. If you have a relation, an equation, x squared plus y squared equals 9, and you want to take the derivative, we've always been finding dy dx. We've been differentiating with respect to x 90% of the time. And that's what we're going to do here. I am going to take the derivative with respect to x. But what I'm going to do is I'm going to do that to both sides, okay? So I'm going to take d dx of both sides and say, all right, well, what's the derivative of x squared? Well, that's going to be 2x, just like you want it to be. What's the derivative of y squared? Well, that's going to be 2y, just like you want it to be. But I'm also going to multiply by dy dx. And if I take the derivative of 9, which is a constant, that's going to be 0. Okay. Real quick, what just happened? What happened is, since I was taking the derivative with respect to x, and then I took the derivative of an x, that derivative works just like normal. If I'm differentiating with respect to x and I take the derivative of x, I just take the derivative. But when I came over here and I said take the derivative with respect to x of a y thing, you have to leave behind dy dx because the letters don't match, okay? That's how implicit differentiation works. And then we say, all right, well, normally we want the derivative. I want to solve for dy dx, and dy dx right now is, in some sense, a variable. So if I want to get dy dx alone, I'm going to subtract 2x from both sides. I'm going to divide by 2y, and negative 2x divided by 2y becomes negative x over y. And now all of a sudden we have derivatives that have x's and y's in them, which is fine. It's totally fine, okay? And then it says use the implicit derivative to, oh, I forgot. It says compare the derivatives found in part C. Sorry about that. I forgot to do the comparison. See, I even made this and I forgot to do it. Let's compare. Is this the same as that? Well, they don't really look it. They don't really look at, well, let's see. So up here for this one, we have dy dx equals minus plus x over the square root of 9 minus x squared, right? If I wrote that. And down here I have dy dx equals negative x over y. Okay, well, I see like kind of the negative part. I'm going to say that these are basically the same. And I see the x, but this doesn't say y, and that does. This doesn't say y, or does it? If I zoom back out, isn't the square root of 9 minus x squared actually y? It is. It is. Those are equivalent. It's just one has all x's because we could get y in terms of x, and the other one has x and y. So they are equivalent. So now we're going to use the implicit derivative to find an equation of the tangent line to the circle in the first quadrant when x equals 1. All right, if I need a tangent line, I need x, y slope. X, 1, cool. Y, well, I got to plug 1 back into the original. So it was x squared plus y squared equals 9. If x is 1, y squared is 8, which makes y plus or minus radical 8. You can make it 2 root 2. I don't care. We wanted the y value, though, in the first quadrant, so I'm going to use the positive y value. And then if I need my slope, that comes from the derivative. Well, our derivative is in terms of x and y, so our slope is negative x over y. And so then when I write the equation of the tangent line, y minus y1 equals mx minus x1. And that is my tangent line. Okay? So implicit differentiation. You take the derivative of x and y simultaneously, but if you take the derivative of y, you have to leave behind dy dx. Okay? And that's what all this stuff down in the box says. Okay? I'm not going to read it. That is there for you to look at later on. If you're like, what do I do if I need to do implicit derivative? Then it's in there. All right. Now, it wouldn't be me if I just told you how to do implicit differentiation and didn't tell you why, so I got to tell you why. So let's go back here for a second, and we have x squared plus y squared equals 9, and I told you that when you take the derivative of that, when you take d dx, you get 2x plus 2y dy dx equals 0, and I just told you to leave behind dy dx because the letters didn't match. That's a really crappy mathematical reason, so I got to give you a better one. Remember when you were in algebra and they first started telling you function notation and they said, you know what, when we use y, we now can also use this function notation called f of x. I'm going to go back to doing that and say, all right, if I have x squared plus y squared equals 9, I should go back to black because it's the original. If I have x squared plus y squared equals 9, that's x squared plus f of x squared equals 9. Okay, cool. And so If I wanted to like take the derivative of this, now I have all x's. That's great. So I'm going to take the derivative with respect to x of both sides, and the derivative of x squared is 2x, and the derivative of f of x squared would be a chain rule. So derivative of the outside, keep the inside, bring down the power reduced by 1, times the derivative of the inside. Yes, yes. Well, now let's backtrack and say, wait a minute, wasn't that just y? Isn't this 2x plus 2y times dy dx? That's why we leave behind a dy dx, is because technically the y is really like f of x. The y is a function of x. The y is related to the x. So when we take the derivative with respect to x of y, a chain rule is occurring. Okay? So that's the y behind the rule that you're really just going to remember, which is if you differentiate with respect to a different variable, you have to leave behind dy dx. Okay, turn the page. Look at this guy. What a cool graph. Okay, doesn't have to be just circles. We can make all kinds of cool things. I can't remember for sure if this is the Witch of Agnesi or not, but some of these graphs get fun names, and I feel like this is either similar to or exactly a curve called the Witch of Agnesi, which is cool. So we can have graphs with loops in them. How fun is that? So we have the curve x cubed plus y cubed equals 6xy, and it's shown right here. Cool. We want to find dy dx. Now, because it says find dy dx instead of the derivative, that's what you're going to get more used to, okay? We're going to tell you what to take the derivative with respect to. So find dy dx means find the derivative with respect to x, okay? So we are going to do that. We are going to take d dx of both sides of this equation. Okay. The left-hand side is going to work just the way you think it will. The right-hand side is going to take a minute, so don't speed ahead of me. So the left-hand side, d dx of x cubed, y cubed. Well, the derivative of x cubed, that's just an x, 3x squared. The derivative of y cubed, 3y squared. But I took the derivative of a y, so I have to leave behind dy dx. On the other side, 6xy is a product of 6x and y. Okay, yes, there's an argument that it can be 6 times x times y, but the 6 is a coefficient, so just squish it to the x, all right? This is a product rule of 6xy. Got to do the product rule. I need to do extra stuff here. So the first times the derivative of the second. The derivative, with respect to x, of y is going to be 1 dy dx. Because the derivative of y, if I just walked up to you and said, hey, what's the derivative of y? You'd probably say 1. But it's a y, so I have to leave behind dy dx. Plus the second times the derivative of the first. The derivative of 6x is 6. Okay. Ooh, I got 2 dy dx's. That's okay. That's okay. We can still solve for dy dx because dy dx acts like a variable. So I am going to take the time here, and I'm going to get all the dy dx's on the left. So that would be 3y squared dy dx minus 6x dy dx equals 6y minus 3x squared. I took all the dy dx terms and made sure that they ended up on the left, and took all the non-dy dx terms and made sure they ended up on the right. Just rearrange the equation. And since dy dx acts like a variable, we can factor it out as a GCF. And then we can solve for dy dx. So dy dx is 6y minus 3x squared divided by 3y squared minus 6x. And there's dy dx.